Hello and welcome back to the lab. Today we're going to take a look at my HP339A distortion measurement set. I put it on the bench so that I could make a distortion measurement on my 200 CD oscillator that I worked on in the previous video, and it worked well for that purpose. So my 339A is essentially working, but it does have a few issues, which I was aware of since I first acquired this instrument, but I wasn't able to take a closer look at what was going on with it up until now. But now would be the perfect time to do so. So let's go. So first, let's take a closer look at this instrument. The HP339A distortion measurement set was made by Hewlett Packard between 1976 and 1992. Um, it's used for measuring distortion, obviously. Um, it was the gold standard for many, many years. If you wanted to measure distortion, you wanted to use an HP339A. It still is to a great degree very valuable instrument today. It really consists of two instruments because it's a measurement set. It consists of two instruments. The first instrument is an extremely low distortion oscillator. And that's represented on the front panel by this section here. It has an output attenuator that goes from 3 volts down to 30 millivolts with a vernier amplitude control, as a vernier frequency control, and stepped frequency control set by these dials up here, from a low of 10 hertz up to a high of 110 kilohertz. It has a 600 ohm impedance output, extremely low distortion, very pure sine wave on the order of minus 100 dB THD, very high quality oscillator. It is in fact a Wien-Bridge oscillator, just like the 200 CD we looked at in the last video. Of course, there are no tubes inside this instrument. This one actually uses op amps and discrete transistors in its analog circuitry. Coupled with the low distortion oscillator is the second instrument inside this enclosure, and that is a distortion analyzer. And that's represented by the input section over here, along with the rest of the dials on the instrument. Distortion analyzer is itself two separate instruments, primarily a voltmeter, which you can see over here. This is an RMS responding AC voltmeter from 10 hertz to 110 kilohertz, very much the same as the oscillator frequency range. Along with the RMS responding AC voltmeter is a tunable notch filter, which uses the same frequency dials up here that the oscillator uses. So the frequency that the oscillator is set to is the same frequency that the tunable notch filter is set to. To use a distortion analyzer, what you do is you input a signal and take a measurement, and then you switch from input level mode to distortion function, and the tunable notch filter will notch out the fundamental frequency of your input signal. And the only thing that's left when you remove the fundamental frequency is the harmonics, or the THD, total harmonic distortion. And that's what the distortion analyzer portion of this measurement set will measure. It can also go down to minus, way below negative 100 dB, below the fundamental frequency. It also has a few other features. There's an AM detector, a simple diode detector. If you can select this, you can put in an AM signal here, demodulate it, and check the distortion of the audio. You can select high pass or low pass filters. A high pass and will cut anything below 400 hertz. There's also a 30 kilohertz low pass filter and an 80 kilohertz low pass filter if you want to remove out higher frequency components from your input signal. Normal or VU responding meter. If you switch it to VU, the meter will respond more quickly to changes in your input amplitude. And that's it. That's basically the instrument here. Oh, the one other thing is you can use the output, the monitor output over here, takes the result, the output of the distortion analyzer, and you can input that into a spectrum analyzer or other similar external device to even further increase the resolution and the maximum dynamic range of the distortion measurement of your instrument. How instrument is generally used is you use the low distortion oscillator as a signal source input into your device under test, which would usually be an audio amplifier or something similar. And then you take the output of that audio amplifier or that device under test and input it into the distortion analyzer. The distortion analyzer will automatically um, look for the frequency of the fundamental frequency of your input signal, and it will, when you switch to distortion mode, it will tune the notch filter to that exact frequency and minimize and notch out that fundamental frequency to its maximum extent, allowing you to measure the harmonic distortion of the signal. So you can measure between the output and the input, you can measure how much distortion your device under test is generating and adding to your desired signal. A good way to test the 339A itself is to simply connect a wire from the output of the oscillator into the input of your distortion analyzer. So you're really checking the distortion of that piece of wire, which will have no distortion, of course, for all practical purposes. It will have no distortion, and so that way you can check both the distortion level of the analyzer itself, as well as the distortion level of the oscillator itself. And you can make sure that the notch filter is tuning to the correct frequency, and so on and so forth. So that's what I plan to do, to see if I can demonstrate for you some of the problems we were seeing with this instrument. Before I get to that, though, I wanted to make a few comments about this unit. They're still highly desirable and highly sought after, and they sell for a very high price. On places like eBay, many of them are going for well over $1,000. I certainly didn't pay anything close to that for this instrument. One came available from a person that lived out in East Texas, about 2.5 hours away from me, and I told him I was going to come to pick it up. So I drove out 2.5 hours, and we made a deal in his little lab in his Radio Shack, and he sold it to me, and I brought it home, and that's how I have it. Many of these instruments are in perfect functioning condition, but most of them have cosmetic issues. Specifically, the plastics that were used in the knobs and in the binding posts and so on and so forth did not stand the test of time. They became degraded and brittle, and many of the knobs are cracked and broken, falling apart. Sometimes they will disintegrate in your hand when you're trying to turn the knob. Unfortunately, HP did not do a good enough job with choosing the plastic materials for use in their instruments. So that's what most of those problems are with this particular unit. You can see a few examples of that here. There's a cracked knob here. I actually super glued a few of these with some CA glue to try to hold them together. CA glue is really not the best product to use on this type of plastic. I consider it to be a temporary stopgap solution to the problem. But replacement knobs for these units are becoming more and more difficult to find, so we have to make do with what we have. If you'll notice here, on this binding post has a red tip. This is a Hewlett Packard binding post, but it came from a different instrument, and I installed this here on this unit because that binding post, that input banana jack, was actually one of the cracked and broken ones. It was basically falling apart. So I replaced it with one that I had on hand. It's exact replacement except for the color, the red color of the tip. The one that actually belongs here is the same color as this one over here, the light gray or whatever color you would call that. It does not have a red tip. So if I find one like that, I will replace this with that color of binding post banana jack input terminal. But this one works just fine, so I'll probably end up leaving that. That is really the only work that I have done on this instrument up until this point. I replaced this banana jack and I glued a couple of the cracks in some of the knobs that were starting to come loose. And that's very typical for these units. All right, let's see if I can try to indicate for you what problems I'm seeing with this unit. I'll be right back. Okay, so what I've done is I've coupled the output through a banana cable, a coaxial banana cable, through a 600 ohm termination into the input of the distortion analyzer. So the output of the oscillator is going directly into the input of the distortion analyzer. Um, Above the input range selector switch, there are two LEDs that illuminate if you have your input range set incorrectly. That is, if you're putting in too strong a signal, the light will indicate, telling you that you have to turn the input range selector one more notch that way. Likewise, if you have too weak a signal, the input range will indicate that you have to turn the knob in the other direction so that you get close to full scale reading on the meter. These indications just tell you how to set the input range uh, selector switch. Similarly, there are LEDs on the frequency dial that, when you have the function set to distortion mode, will tell you if your frequency is not set correctly. The notch filter frequency is not set close to the fundamental frequency of your input signal on the distortion analyzer. Now, when I'm using the oscillator itself as the signal source, the frequency the frequency of the notch filter should always match the frequency of the oscillator. And in several instances with this setup, with this unit, it does not. And let me see if I can show you that right now. On some frequencies, there's one, 1 kilohertz range with 1 kilohertz dialed up. It tells you that you are not set to the correct frequency because we have an LED lit. That should never happen because the oscillator frequency and the notch filter frequency should always be the same. Those switches are ganged internally to rotate, to set the frequencies simultaneously to the same frequency. And there are several combinations of those which tell you that those frequencies are not the same frequency. This should never happen when you have the output of the oscillator connected directly to the input of the distortion analyzer. Some of them work just fine. Some of them do not. So I don't know if the problem is dirty switch contacts, some kind of hardware failure inside the instrument, something else going on. I really don't know. Another thing that I have noticed is the distortion that you measure when you're looking at the oscillator output directly should be way down low. It's actually reading minus 86.7 right here. The spec, it has to be below minus 90. And in fact, it's always well below minus 90, or like minus 105. Now, you can't really read 105 on here, but you can take a look at the output through the monitor onto a spectrum analyzer and get well down below 105. In this case, it's not reading low enough for that. This measurement is slightly out of specs, slightly out of spec, um, and several of the frequencies are showing that same problem. So I don't know if these two problems are really the same problem. I'm not really sure. One thing you can do is click in the filters, the high pass or low pass, to see specifically. Sometimes if the problem is hum, like ripple on the power supply lines or something like that, or somehow hum induced in the system somewhere, if you turn on the high pass filter and notch out that frequency, that 60 hertz or 120 hertz hum, um, your reading will change. It doesn't look like that's the case. So perhaps the problem is not hum. It's slightly out of spec, and I don't know, but it looks like the notch filter, fundamental notch filter frequency, is not doing a good enough job. It's possible that it simply needs to be realigned. There are adjustments for that inside the instrument. So let's open it up and take a look and see if maybe we can find out what's going on there. Okay, first you always want to unplug your instrument. Safety first, you don't want to get zapped. I believe on this unit that most of the circuitry is on the underneath side of the instrument. So we're going to flip it over, and there's one screw in the back. If you loosen it, bottom cover should come right off. And there we have the guts of the unit. Okay. Let's turn it around. Let's zoom out a tiny little bit. It won't zoom out. Zoomed out all the way, I guess. Okay. All right. We have power supply circuitry over here, of course. We have range selection switches over here. Inside the cover is the oscillator section, and behind that is the notch filter of the distortion analyzer section. We have the function rotary switch over here. Lots of interesting circuitry in here. There's a relay. Not sure what that's for. Anyway, and we have, this is the notch filter board right back here that does all the notching. I was thinking that we might simply have dirty switch contacts in here. That's possible. This instrument doesn't have a fan, so it's not blowing dust in. So there's not a lot of dirt inside the unit, but there may be some corrosion or some dirt, some kind of contamination on the switch contacts. Let's take a closer look at that. Oh, let's remove the bottom cover of the oscillator. Someone has been in this instrument before. These screws are supposed to be posi drive screws, and they are not posi drive screws. They are, in fact, standard Phillips screws. Hewlett-Packard would not have used Phillips screws in that time frame. Those are the wrong screws. Someone has been underneath this cover before, and they replaced these screws with the wrong ones. So I got a feeling that all our problems might be underneath this cover. It's possible. So let's open that up and see. Oh, strange. Screws aren't even the same length. One short one, one long one, and they're both wrong. How about that? I can probably find some replacement screws to put in there that are the correct posi drive. All right, let's open this up. Um, Take a look at those switch contacts. Yeah, you probably can't see, but there's somebody has applied some kind of goop onto these switch contacts. Yeah, they're kind of gunked up with something. I'm not sure what that is, but let's see if we can't do something about that. Now, in the past, I've used standard Q-tip to get in there and clean the switch contacts with some switch cleaner. I have a couple of different types, including the standard that everybody uses, the Deoxit D5. It's really good stuff. I don't like spraying that down in there because it gets everywhere and it actually adds a lubrication to your switch, which I don't really want to have. Um, I can use this, I tend to use this by spraying onto the Q-tip and then using that to clean the contacts. The problem with the Q-tip is sometimes the cotton fibers come off of the Q-tip and adhere to to the switch contact, making your problem even worse. So I found these online, these foam tip swabs that use for cleaning. I don't know what they're really used for, cleaning camera lenses or something, I suppose. Um, the tips are much larger than a Q-tip, so sometimes they're hard to use. But I've used them the past few times I've tried to use them. They seem to work as long as you can get into the switch contact. So I'm going to try to use this foam swab to clean the switch contacts, and we'll see how that works out. So we'll pause the video while I work on that. Okay, so let me show you what I found. This is what a new clean foam swab looks like. After working on this for a minute, this is what we found. Some kind of gunk. And in fact, this is not what we found. This is what we found. I had to go through all of these cotton swab or foam swabs in order to clean whatever that gunk was off of the switch contacts. None of that stuff should have been there. Whoever was in here before put some kind of gunk on those contacts in an attempt to clean them or lubricate them, or I really don't know. Um, I mean, I kind of doubt that this has solved the problem, but it's possible. But in any case, all that stuff had to be removed. Um, Pretty gross. Pretty gross. All right, let's turn it on and see if anything has changed. Okay, so I plugged it in and turned it back on and connected up the output to the input again, like before. And I don't know if you can see this. Hopefully you can. The out of frequency range indicator light is still lit. All right, so we haven't solved that issue. Now I did notice, however, that our indication on the meter has dropped by about 2 dB. So it has gotten slightly better, slightly better. In fact, it probably actually meets spec now, even though the the uh, the out of frequency indication is still lit. So I don't know if there's something wrong with the control logic or whatever for this indicator light. I don't think so because it only happens at certain frequencies. But we could take a look at that. what I usually like to do is first look at the power supplies and make sure that they're okay. And I also want to perhaps see if maybe we can't just do a realignment to bring it closer into spec, or maybe get these lights to turn off the way they're supposed to. So let's get started with that. So looking at the schematic for the power supply, um, something I had forgotten about. I used to work on these instruments back at HP, but I had forgotten about this. The oscillator power supply is completely independent from the analyzer power supply. So they are indeed two separate instruments inside of one enclosure, including the power supply. So um, the oscillator power supply has a plus and minus 15 volt that's generated by a single regulator chip. And the analyzer power supply looks like it uses the same regulator chip to control a couple of pass transistors to give you also plus and minus 15 volts. So there's separate 15-volt supplies for the analyzer and for the oscillator. I guess you need to supply additional current to the analyzer, so that's why they have pass transistors in here. So let's find these test points and make the measurements and make sure that our power supplies are where they should be. So the oscillator power supply, negative 15 volts, reads minus 14.81. That's probably okay. It seems a little low, but it's probably okay. The plus 15 reads plus 14.81. Very good, very good. They match exactly. The other supply is over here. Let's see if we can't measure that one. I think we can go off of ground here. Wait, let me stop the camera and see if I can't figure it out. Okay, now the other supply for the analyzer, plus 15 reads minus 15 reads minus 15.24, and plus 15 reads plus 15.36. Those seem a lot closer to correct. All right, let me look in the book and see what it says for tolerances on these power supplies. All right, well, I didn't see anywhere in the manual where it says anything about uh, the tolerances on the power supply rails. In any case, there are no adjustments anywhere on this board to adjust the power supplies. What I did do is disconnect this plug, which supplies the power to the oscillator assembly. Um, and while measuring these voltages, and they did not change at all. So I assume that this regulator is working properly, and there's nothing on the oscillator board that may be pulling that voltage down slightly. Now, likewise, I did the same thing for this connector assembly, and those voltages did not change either. Um, but some of these voltages are actually connected through this jumper that's hardwired in the instrument to other parts within the same board. So not all of the power supply was disconnected when you unplug this jumper, this plug. But in any case, this power supply already reads higher than plus 15 and higher than minus 15. So I assume there's nothing wrong with any of the power supplies, and we can move forward. Oh, the other thing I did check was the ripple on the primary side to take a look at these 1,000 microfarad capacitors. I assume they were probably okay, and it seems to me that they're fine. There's no ripple on the input side of the regulator either. So ripple is not the problem. Power supply levels are most likely not the problem. Um, just cleaning those switches seems to have made a difference, but we have not resolved all the issues yet. But it looks like I'm running out of time in this episode, so we'll have to continue our troubleshooting in the next episode. Thank you very much for watching. Please like and subscribe, and stay tuned for the next installment on the 339A repair. Thanks again.